All right. Well, good afternoon, and welcome to week 10 out of 10. So this is our last week of CSE222. And we got two classes this week. Today we're going to talk about sorts and heaps and finish up all of that. And then Thursday I'm planning to spend on just review and questions and maybe a few comments about the final exam and such. So any questions from anyone up front?
Are we going to be able to do like a PA5 thing on Thursday?
What sort of thing?
Just like, normally after we're done with the project, you'll go through and show like how you did some of the things just to get us a better idea of maybe some better ways to do it.
I can do that unless there's still people who haven't turned it in, which is a possibility. But if I don't get to that, we can certainly do that in office hours.
Okay.
Yeah.
All right. Sounds good. Thanks.
Okay. Any other questions? So I will probably end class about 5 minutes early today, so that we can get to the SLP Zoom room, because those start at 3 o'clock and I want to get there a few minutes early to help set up. So we'll probably end about 5-10 minutes early today, I think.
I did want to ask that too. Is the link in the calendar description there?
It should be in the description on Canvas.
Okay. Perfect.
Mm-hmm. All right. Well, let's talk more about sorts. So we reviewed bubble sort last week, and bubble sort is a series of passes through your data that basically move the largest unsorted item into the proper position at the end of the list each pass. And so you take n passes through, and your data ends up sorted, and each pass is roughly n operations, the length of the list. So that's an order n squared operation. There's two other really quick sorts that are also order n squared. The first one is an insertion sort. And insertion sort work like this. The other one's going to be selection sort. And it can be hard to keep straight which is which. So I'll tell you how I think of an insertion sort. So let's have some unsorted data. And so this is our input data, and we want to create an output set containing the sorted version of this input data. Okay, an insertion sort works as follows. We simply take the first thing from the input list and we copy it to the output list. And since our output is empty, this 4 is just going to go right in the beginning. And then we move on to the second thing in our input, and we put that into the proper spot in our output list. So in this case, we would insert this, before the 4, and so our output would look like 2, 4. And then we go to the third thing, and that's a 1, and so we're going to insert that before the 2, and so our output list will look like this. And then we go to the fourth entry in the input, that's a 7, and that can just go at the end, and so on. And so this is basically like what we did with our linked list back in the very beginning of the course. You had a list that was keeping your numbers in sorted order, and each time you wanted to add a number, you simply found the right spot to add it. And so if you wanted to build a sort algorithm out of your PA1, all you'd have to do is take your input data and just one by one add it to a list using your add function. And then when you're done, if you traversed your list, your data would be sorted. So that's what we call an insertion sort. And the kind of sort of a dual to that is a selection sort. And this is also order n squared. But with a selection sort, what you do is, you're creating an output list. Let's use the same input list. You look through your entire input array and you find the first thing that you want to put into your output. So you find the smallest thing in here, which is, for example, the 1, add that to your output. And now you go through and you find the smallest input value that you haven't already used. That would be a 2, and you put that on your output. And now you go through and find the smallest input value you haven't used. That would be a 3. Add that to the next spot in your output, and so on. So the difference between these is where you're doing the work, where the sorting is happening. With an insertion sort, the sort happens when you insert into the output. With selection sort, the sort is basically happening when you select which thing from the input to copy to your output. So
Would you say that's kind of similar to like our inventory on PA5, which is like take a note of which one is the best, but in this case it'd be which one's the smallest?
Yeah.
Put it in at that point.
Right, so you could go through and instead of best, you could have worst and find the smallest number here. And then whichever one you end up with, if that was at index 2, you just copy that into your output. So neither of these is too hard to code other than, the quirkiness of dealing with arrays in some languages. But an insertion sort is fairly straightforward. We've done it with PA1 basically, with a linked list. But if our output was an array, we would look through the array, we'd find the right spot. So say we were doing the 3, we'd go through here, we'd see the 3 should go right before the 4. We'd run a little loop to copy all of these things down one spot in the array, and then we put the 3 right where that 4 was. Or we can do the linked list. And those are both, order and operations. So inserting one number into the output is order n. Deciding which number you're going to insert is order 1, right? We just take the next thing from the input list. So we start off with the 4 and the 2 and the 1. The next thing would be a 7. The next thing would be a 9. So we're just sequentially going through the input. That doesn't take any time. The work is when you insert into the output. That's order n. And we have to do that for each of the n numbers. So this is n times that we have to do order n work. So this is order n squared. With a selection sort, adding to the output takes no effort. You just have an index saying where's the next location in the output array, and whichever number I select, I'm just going to pop that into that location, bump up my output index. But to find the smallest thing in this array, that's an order n operation. I have to go through and look at each number compared to the smallest I've seen so far. So we do an order n operation, and we have to do that n times to create n output values. And so this is also order n squared. And so these are on par with a bubble sort. All right, so good for a quick and dirty implementation, but not good for, a trillion pieces of data, which would take, 10 to the 24th operations, and I don't think there's that many milliseconds in the expected life of the universe. So not a good sort choice. We kind of use these things in daily life, though, when we have to do sorting tasks. For example, when you have to alphabetize a set of things. So when I'm grading, I have to alphabetize papers so that I can enter them in Canvas, because Canvas is alphabetized, right? And so I looked at this once and tried to figure out how I do my alphabetizing, and it turns out I do basically an insertion sort. I take papers from the top of my input stack and I place them into an output pile in sorted order. And so I just pull, the next paper off the top, but I decide where does that go in my output. If it's a P, it goes, between M and R. And so I seem to do an insertion sort. But it's not a good proposition, right? If I had 60 papers that I needed to sort in order to put grades into Canvas, I end up doing 3,600 operations, roughly. It's probably half of that. But, a few thousand operations just to alphabetize papers. And if it takes 10 seconds to pull one paper out and figure out where it goes in my output pile, that's 10 hours. So this is not an efficient sort. Because, you got to grade 60 papers. You don't want to spend 10 hours just alphabetizing them so you can record the grades in Canvas. So we'd like to do better than this. And so we're going to talk about a series of sort algorithms that are better than n squared. The first one being a merge sort. And merge sort will actually be order n times log n. And that's a much nicer number. If I increase my data by 1,000, I increase my computation time by about 10,000. So not quite linear, but sort of close. And it turns out when I'm grading papers and I'm alphabetizing them, I don't do the 10-hour insertion sort. I do insertion sort on, say, a quarter of the pile. So I get a quarter of the pile alphabetized, and then I do another quarter of the pile, and another quarter, and another quarter, and I end up with 4 piles that are each alphabetized, but I need to put them together. And I do that by basically mixing them together. So here's an example of a mixing operation. So suppose I have one set of numbers, which is sorted. So 2, 10, 12, 18, 25. And I have another pile of numbers, which is, 1, 9, 11, 17, and 30. And I want to combine these to make a list of 10 numbers, sorted from smallest to largest. Well, all I ever have to do is look at the top number of each list. I look at a 2 and a 1 and I say, which of these is smallest? It's a 1, so I write down a 1. And now I look at the top number of both lists. And a 2 is smallest, so I write down a 2. Look at the top number of both lists. A 9 is smallest. Write that down. Look at a 10 and 11. There's a 10. Cross off the 10. Look at a 12 and 11. 11 is the smallest. Look at a 12 and 17. 12 is the smallest. Look at 18 and 17. 17 is the smallest. Look at 18 and 30. That gives us an 18. Look at 25 and 30. That gives us a 25. And now there's nothing left in this list, and so I just put the last number from the other list into here. And there's my sorted list.
So this would work if you had one list that was like 1 through 5 and the other one that was 6 through 10 too, right? It would still compare the top, but it would only remove from the one list and then eventually go to the other list, right?
Yeah. And you need some sort of way to do what I'm doing so easily on paper, which is, crossing out, okay, this is the top number of that list. That doesn't work so well in C unless you use some structures and some flags or something like that. But the spirit of it is very straightforward. The spirit of it is simply, you have 2 lists. Let's just keep taking the top thing from each list and comparing them. Whichever one is smallest, we'll move that to our output. And so if I have 2 stacks of 15 papers, I have to do a total of 30 operations, 30 comparisons basically, to mix those together and generate a sorted list of 30 papers. And then I can do that on my other 2 stacks of 15 and get another stack of 30. And now I have 2 sorted stacks of 30 papers each. And with 60 comparisons, I can combine those into a final sorted stack of 60 papers. And it's much more efficient than, you know, doing 3,600 operations for a bubble sort or an insertion sort. So this mixing business is the idea behind a merge sort. And mix is, you know, order n. Because you go through your n pieces of data, and comparing 2 numbers takes a fixed amount of time. Doesn't matter how many other numbers I have in the list. Comparing these 2 numbers, picking the smallest, copying it to the next output location, it's a fixed amount of time. So it's just a matter of how many times I do that comparison. That's order n. So here's how we use that to do a merge sort. So I'll call this m sort. And I'll just make data. So this will be pseudocode. So data is my collection of data. So I got 3 steps. I got a few steps. So set A equal to first half of data. Set B equal to the second half of data. And if there's an odd number of things, you know, one of them will be a little bit longer than the other. But basically break my data into 2 pieces. I'm going to set A to that first piece, B to that second piece. And then I'm going to sort that first half. I'm going to sort that second half. And then I'm going to mix those 2 sorted piles, right, using this mixing idea, and set data equal to the result. So here's the $1 million question. How do I sort these 2 smaller sets of data? What would be a good sort to use?
Well, you could do a bubble sort or an insertion sort when the data is, like, the array is created, right?
So I could do a bubble sort or an insertion sort or a selection sort. But those are order n squared sorts. And I've claimed that merge sort is going to be n log n, which is a lot better. And if you believe me that that's the case, then let's go ahead and do a merge sort on those sublists.
Would we recurse them back onto the, well, per one?
So we'd recurse. So the merge sort algorithm is the following. Split your data into 2 sets, call merge sort on each of those subsets, and then mix those 2 sorted lists back together again, and you're done.
So basically that's going to keep doing it until it says everything is sorted correctly, basically.
Yeah, so we need a base case. So let's put our base case in here. If the data you're asked to sort consists of either 1 number or no numbers, just return. There's no work to do. We don't have to split, we don't have to recurse, we don't have to mix. If you have a list with numbers and there's only 1 number in the list, it's already sorted. So if the length is less than or equal to 1, we'll just return. Otherwise, split your list in half, sort each half, mix them together.
Could you also do like a boolean function with that too?
Like what?
Check and see if it's sorted and return true if it is.
Checking to see if something's sorted is an order n operation, so we probably don't want to do that unless it's really, really necessary.
Okay, so that'll take down productivity overall.
Probably, yeah.
Okay.
And we may get lucky and find, you know, that at some point we have a sublist of 2 elements and it's already sorted. but it's almost as efficient to just go ahead and keep recursing. Although if you have reason to believe your data may be largely sorted to begin with, it might be worth doing something like that. So it's,
I think I'm still trying to get recursion and like the process of recursion going.
so let's do an example and see what this looks like. So I'll pick on our insertion selection sort example for no reason. Alright, there's our input data. So what does our merge sort do? It says split this data into two lists, sort each of those lists, and we're going to do that sort by calling this magic function called msort. Right? So this is A, this is B. We're going to call msort on A. We're not going to think for a moment about what happens when we do that. We're just going to believe that, you know, since the comments in the beginning of msort say this will sort your data, then when we come back, A is going to look like this. 1, 2, 4, 7. And then when we call merge sort on B, B is going to come back and it's going to look like this. So this will be our sorted B, this will be our sorted A. And then we're going to mix these, which will say, look at the 1 and the 3, we'll take a 1. Look at the 2 and a 3, we'll take a 2. Look at the 3 and a 4, we'll take a 3. Look at the 4 and a 6, we'll take a 4. Look at the 7 and a 6, we'll take the 6. Look at 7 and 8, we'll take the 7. And now there's nothing left in A, so we'll just take the rest of B. And bingo, there's your sorted data. So that's the view from, you know, just one pass through this without worrying about what happens here. But if we want to know what happens here, let's do this again and let's follow the recursion. So our input data is 4217 9836. And this is A and this is B. And we say msort A. Alright, so we're going to call merge sort. So this was our original call, which was trying to sort all of this data. So we're going to make a recursive call to merge sort on this smaller set. So we're going to say let's msort 4217. Alright, I'm putting this call on my stack. And now we're doing this version of msort. So what's msort do? It splits your data into two pieces. So this is A and this is B. And then it calls msort on A. Got another recursive call. So we're going to say, okay, let's call msort on 4, 2. So I'll put this on my stack. And what does msort say? Well, it says split your data into two pieces. Call the first piece A, the second piece B. And then call msort on A. So we got one more recursive call. We're going to call msort on 4. And the beginning of our msort function says if the length of the data is 1, return. So this call returns right away. And our data just looks like 4. Alright, so we're back from our call to msort of A, now we have to msort B, and the same thing is going to happen. We're going to come back, and B is still going to be 2, A is going to be 4, and finally we're going to say mix these. And so we mix these, start off with the top number in each list, smallest one is a 2, so that goes in the output, and then the other list goes after that. And so this is what's returned by the call to msort 42. So it returns 2, 4. So we go back to the top value on the stack. And we just came back from msort 2, 4. Or 4, 2, and that gave us 2, 4. And then we're supposed to msort B. And so same idea, right? We'll make a recursive call to msort 17. And this will get split into A and B, and we'll call msort, and msort will return exactly those values, and we'll mix these, and we'll get a 17, and so msort B will return 17. And so we've msorted A and B, and now we mix these together. So take the smallest from the top two items, that's a 1. Take the smallest from the top, that's a 2. Take the smallest of these, that's a 4. And then there's a 7. And this is what this call to msort returns. So we finally pop our stack back to our first call frame. And what we had just done was split our set into A and B, and we just called msort A. And that returned 1, 2, 4, 7. Now you repeat all of that again to find msort of B. And you go down that whole recursion tree, and when you're done you come back, and eventually you'll find out that, you know, msort of B returns 3, 6, 8, 9, and then you do your mix, and you're done with your call to msort of all of this, and there's your sorted data. So tracking the recursion is tricky. Writing down this algorithm is pretty simple though, right? As long as we believe this will sort A, this will sort B, then splitting your data in half, sorting each half, mixing them together will sort the entire original set of data. Alright, so your mixing operation, that's order n. Splitting your data in half into two sets A and B, that's just a fixed amount of operations. Calling msort by itself is you know, it's the time to do a function call, that's a fixed amount of time. So the real question is, how many times do we call msort recursively? And we know that each time we go into msort, we're going to end up doing order n work when we mix. But how many times do we recurse? Well, each time that we call msort, we're calling it on an array of data that's half the size of the original. So if we started with msort of 8 items, we have to make a pair of calls to msort of 4 items. And so each time we call msort, our data gets split in half. And we keep recursing until our data has length 1. And so how many times can you cut something in half until it's equal to 1? That's roughly logarithm base 2 of n. So this is how many times we call msort, and each time we call msort it takes order n. And so a full merge sort is order n log n. That's an approximate calculation. You can do more work and make that a little more precise, but that's the spirit of it. The bulk of the work is in mixing things together, and you simply do that a number of times based on the log of the number of items in your original list.
How much worse is O n log n than O log n? Like
N times.
yeah.
It's quite a bit worse. I mean, if n was a trillion, right, n log n will be a trillion times worse than just log n. So for large data, it becomes significant, but it's pretty hard to imagine doing something to n pieces of data without needing at least, you know, n amount of time. So binary trees, right, we can insert and we can delete and we can search in log n, and that's pretty remarkable. But it's because the way that the tree is set up, we don't need to deal with most of the data, right? The divide and conquer nature of it is saying we're throwing away half our data each time we move down the tree. But to do something like sorting, we really need to touch every piece of data. And so it's hard to imagine a sort that's going to do better than n. And so n log n is kind of, you know, a about as good as we probably deserve to expect.
Yeah, it just I was more so asking relative to probably ON squared, but
so compared to n squared, this is a lot better.
okay.
Because, you know, even if n is like a trillion, log n is only 40. So this is a relatively small constant compared to n or n squared. If n's a trillion, n squared is a trillion, right? That's 10 to the 24th, as opposed to, you know, 40 trillion, which is 4 times 10 to the 13th.
Wait, no, I got that wrong. You're right. Interesting.
Yeah, so merge sorts are pretty good, and they're pretty fun to code. Other than, you know, like in C, arrays are kind of a pain to work with, as you've probably noticed in PA5. In other languages, you know, we may be able to do something like just say, you know, use data 0 ... length over 2, and use data length over 2 plus 1 ... length or something. But not so comfortable in C. But that's not the algorithm's fault. That's just languages. All right. Let's talk about a very different kind of sort. This one's going to feel probably significantly different from a merge sort or from insertion or selection. This is something called quicksort. And quicksort is a quirky sort. Let me go through some of my stack frames here. So let me give you a set of data, and I'll tell you how quicksort is going to work. So here's a set of numbers. So I got 12, 23, 11, 14, 60, 55, 8, 1, 19, and 17. Alright, so we got 10 numbers. So quicksort begins by picking one number, and this number is going to be called the pivot. And typical algorithm, we pick the last number in the array to be the pivot. So I'm going to draw a box around the 17, and I'm going to label it pivot. Alright, so here's the goal. We want to rearrange this array of numbers so that wherever 17 ends up, everything to the left of that position is smaller than 17, and everything to the right is bigger than 17. And we're not going to worry whether the stuff to the left is itself sorted or the stuff to the right is sorted, but we want to rearrange things so that wherever we put the 17, everything to the left is smaller, everything to the right is bigger. And I'm assuming there's no duplicates here, as with most of our sorts. So if we were to peek ahead, right, and look at our sorted data, this would be a 1, 8, 11, 14. The 17 probably wants to go right here. And then 1, 8, 11, 14 have to go somewhere on the left. And the 12 also. And then the other numbers have to go to the right. Alright, so quicksort is going to work as follows. We're going to do an operation to move the 17 into the right spot in the array, have everything to the left be smaller, have everything to the right be larger. And this is the main work of a quicksort, is putting 17 into the right spot. Alright, so goal. Move 17 to proper spot in array so that all numbers to the left are less than 17, and all numbers to the right are bigger than 17. And we want to do this efficiently. We want to do this in order n. So here's the algorithm. We start off with the first number, and we're going to have an arrow here which is going to move through the array. And we want to see if the number that we're pointing to is smaller than the pivot. And if it is, then we're going to move on to the next number, and we're going to see if that number is smaller than the pivot. And it's not. 23 is bigger, so we're going to stop. Alright, now we're going to do a similar operation from the right, and then we're going to be done. Alright, so what do we do from the right? We look at this first number, and we're hoping this number is bigger than the pivot. And it is. 19 is bigger than 17. So we move over one spot, and we find the number 1. And 1 is not bigger than 17. 1 is smaller. So we stop. Okay, as soon as you've done this, you've moved from the left, stopped when you found a number too big, moved from the right, stopped when you found a number too small. Now we're going to go ahead and we're going to swap those two numbers with each other. So we're going to take this number and swap them. And this is going to give us a new array of numbers: 12, 1, 11, 14, 60, 55, 8. There's our 23, 19, and 17. 17 is still the pivot. We keep our indices intact for how we were looking at data. And now we go back and we do this again. So we just did the 1, so move to the next number. There's an 11. 11's smaller than 17. Good. Move to the next number. There's a 14. That's smaller than 17. Good. Move to the next number. There's a 60. That's not smaller than 17. Stop. And now go from the right. This was the last number we looked at. Move to the next number. And we're looking for things to be bigger than 17. And 8 does not satisfy that. 8 is not bigger than 17, so we stop. And as soon as you stop, we swap these two numbers with each other, and we come up with a new output array. So the 8 goes over here, the 60 goes here. This is still our pivot. I'll remember which numbers we've already dealt with. And we go back and we do it again. So take the left index, move that. That's bigger than the pivot, so we stop there. Now go to the numbers from the right and move over. And at this point we notice our two indices have hit each other. And so we're done with that part of the operation, and now we simply swap this with the pivot. And so our final array will be 12, 1, 11, 14, 8. The pivot goes over here. These numbers stay the same, and the 55 went out where the pivot was. And now I'm going to circle the pivot. Okay, so what's happened? All the numbers to the left of 17 are smaller than 17. All the numbers to the right are bigger. Right? This is guaranteed to be the case now. Because what did we do? We moved over until we found a number that was too big. We moved over until we found a number that was too small, and then we swapped them. So the smaller numbers over here, the bigger numbers over here, we kept going until we got to another spot where our numbers were out of order, and we swapped those.
So we're more so looking for just a spot to take the pivot, not necessarily sort the whole array.
Yeah, and the array is definitely not sorted. I mean, there's a 60, 23, 19, right? But the 17 has been placed somewhere, and things have been moved around so that everything over here is less than 17. Everything here is greater. But what that tells us is... Go ahead, say again.
What was this called again?
This is a quicksort.
Quicksort.
Yeah. Not so quick to explain, but really quick to run. So what's happened is, with the 17 being here and everything over here being smaller, everything here righter, the 17 is in its final position in the fully sorted array. right? Once this array is totally sorted, we know that everything to the left will be smaller. Well, this is everything to the left. If there's 5 numbers that are smaller than 17, 17's got to be in the 6th position. So the result of doing this one pass is to put one number into the correct position in the output array.
So, let's say we wanted to sort an entire array with this algorithm. Probably could, right?
Yeah.
Would it be any particularly faster?
Well, so here's the question. Our array is not sorted. We've only got one number in the right spot. So how are we going to sort these subarrays? If we sort this and we sort that, then we're done, right?
It's still potentially an ON, I guess, then, right?
It's ON to do one of these passes, right? We're starting from one end and moving over, and then starting from the other end and moving in. And we may move in different ways, but we stop when both arrows reach each other. So we're going to do n operations for one of these passes. And we've got one number in the right spot. But to finish sorting, we have to sort this smaller array and we have to sort this smaller array. And so what's a good sort algorithm to use to sort this and to sort that?
It would be a merge sort.
Could do a merge sort. What else could we do? We could do a quicksort, because we love recursion, so why not? So this is how quicksort works. You make a pass to move your pivot into the proper place, and then you quicksort everything to the left, and you quicksort everything to the right, and you're done. Easy to describe, tricky to code. But it's another good old recursive algorithm. And again, you know, each time we move the pivot in, we basically cut our list in half. And so the total number of times we'll have to do this will be roughly log n. And so this will end up being another order n log n sort. But potentially not as much data movement as some other sorts. We flip things around when they have to go on the other side of the pivot, but we're tending to localize data more. All right, so let's sketch something like some pseudocode for this. So here's qsort. And I'm going to be kind of approximate with the pseudocode because I don't want to get into like n-1 versus n-2 for indices and things like that. So this is going to be pseudocode, right? But quicksort, you know, n pieces of data in an array called data. So we can do something like this. Left equals, you know, 1. Right equals n-1. Pivot equals n. So yeah, I'm indexing from 1, that's okay. So this is our first piece of data, and left is going to be where my left arrow is pointing. And right is, you know, this n-1st piece of data, that's where the right arrow is pointing. And pivot is just, you know, the last thing in my array. And so let's move the left arrow. And so we could do something like, you know, while data bracket left is less than data bracket pivot, so if this number is smaller than the pivot, then let's just increment the left pointer. So move it over to the next number and so on. And remember, this whole thing's going to end if our left and right arrows ever meet up with each other. So I'm going to say, well, data left is less than data pivot, and left is not equal to right. I'll move the left arrow over. And then once we had to stop with the left arrow, like we got right here, we're going to start with the right arrow and move over as long as our numbers are bigger than the pivot. So now move the right arrow. So while data bracket right is bigger than the pivot and left and right haven't collided, let's decrement the right arrow. So I'm just doing right minus minus. So now we're moving our right arrow over. And then we can say if left is not equal to right, if left is not equal to right, swap data left and data right. So do this operation where we switch places there, and then go back up here. Move the left arrow again. So big loop. So something like that, right? See the algorithm, start moving the left arrow to the right until you find something in the wrong spot. Move the right arrow to the left until you find something in the wrong spot. Assuming your arrows haven't collided, swap those two elements, go back up, start moving the left again. But when you get to the point where your two arrows collide, we're done with moving the arrows. We want to swap the pivot with that number. So here we're done. And so what do? We say swap data, and I could use left or right here because they're equal. So swap data left with the pivot. So that does that transposition. So now our list looks like this. And now we need to sort these numbers and these numbers. And I'm going to do that with quicksort. So we do some recursion, and I'll say qsort data 1 to left minus 1, and then qsort data left plus 1 to n, and we're done. So for us trying to do this on paper, the challenge is, knowing how to move the arrows and so on. Now I will not ask you to code this on the final, but I will, expect you to know the algorithm and possibly be able to work through some steps of the algorithm on paper. And so let me work through another example of this right now.
Possibly know the...
Say again?
What? You'd possibly have to know the orders of complexity for the final, so OM log n.
Yeah, I'm probably not going to ask that because that feels like memorization, I might ask you conceptual questions about orders, like, which would be faster in the long run, n squared or n log n, something like that.
No, real quick, when you say work through problems like on the final, do you mean like have code there and like what would the output be kind of thing?
So for sorts, I would probably do something like this. I would give you a list of numbers and I'd say show me how the list gets changed as you move to putting the pivot in the correct position. And so something like this. Here's a set of data. So 431, 851, 1837, 11, 7, 9, 20, Alright, so for us, we're always going to take the pivot to be the last thing. And we're going to have a pair of pointers, right, that look like this. And so what do? We move the left until we get to a value that's bigger than the pivot. So 4 is smaller, so we can move the left over to here. 131 is bigger, so we stop. Now we start from the right and we move until we get to a number that's smaller than the pivot. Well, 9 is smaller than the pivot, so we stop right there. And we swap these two numbers. And so after our first swap, this is what our array looks like. And now we go to the top of our loop and we continue. We move the left arrow as long as our numbers are smaller than 20. So 8 is smaller than 20, good. 51 is bigger than 20, we stop. Now come to the right. 131 is bigger than 20, that's good. 7 is smaller than 20, so we stop. And now we have to swap these two. And so our next value of the output array looks like this. And we had 2 arrows here, and we had 4 arrows here. And we go to the top of our loop. So move the left as long as our number is smaller than the pivot. So 7 is smaller, 18 is smaller. So we can do that. Come to 37. 37 is too big. And now we move as long as our numbers are bigger than 20. Well, 51 is bigger than 20. Come to an 11, that's too small. So these two have to swap with each other. And so now our array changes to this. And go back to the top and do it again. So move our left arrow, 11 is smaller than 20. Move our left arrow to here, and at this point, our left and right arrows have met. And so we are done with that loop, and now we just have to swap this with the pivot. And this gives us our final output array. So the 20 comes over here, and the pivot goes, the number there takes the place of the pivot, and now this pivot that we just moved in, this is in the correct spot. So this is what the quicksort algorithm would do to our input list as it works to move this pivot into the proper spot. And it ends up swapping 1, 2, 3, 4 pairs of numbers. Nope, 3 pairs of numbers. And then when our arrows collide, it swaps the place where the arrows met with the pivot, and here's the output. Now if we were being recursive, then we would say, okay, now we call a quicksort on this, and we call a quicksort on this. And we would do the same thing again, right? We would just start with this list, we'd make 11 the pivot, we'd start from here and here, and we'd move and so on. And it's not something we really want to do by hand to a high degree, but that's the idea.
So, is there any real desire to do this over a merge sort?
I think this moves the data less than a merge sort might. I'm not positive about that.
What do you mean by that?
So a merge sort, the business of interleaving your numbers feels like it entails moving all of that data into a different location in memory. And moving data around in memory has an efficiency penalty. If we're thinking about large amounts of data, if you have 1 trillion bytes of data, the cache memory in your CPU is relatively small. It might be, megabytes. And the only reason that you get, something like 3 gigahertz performance out of a processor today is because the data you're accessing is mostly in cache. And so any algorithm that sort of violates locality of data, anything that would take a large amount of data and move it around wildly different locations in memory is going to suffer serious performance issues because your CPU will be throttled. You're going to get basically memory stalls from the memory subsystem because you miss cache, and that's going to be what kills your performance. And your 3 gigahertz machine ends up running at, you know, some number of megahertz instead. And so I think that a merge sort and quicksort will have a difference in terms of how much the data moves, because here, you know, you're moving a relatively small number of pieces of data and you're swapping them, and you've got a bunch of access starting here and a bunch of access starting here, and you're going after sequential locations. But the question is, you know, a much more general one, which is how do you pick one sort over another? Thank you. And it depends on you know, the nature of the data and you know, how your memory behaves and so on and so forth. But let me show you when to not use a quicksort. And this is a bit of a pathological example. Suppose you have data that looks like this.
So if it's already in a sorted order, don't call it.
If it's already in sorted order, you've got a problem, because if we make this our pivot, and we start here and here, and we're looking for things that are smaller than 41, well, this is good, this is good, this is good, good, good. Come up here, our arrows collide, and they collide moving from the left, right? So our pivot is in the correct location. And so now we're going to call quicksort on this set of data, and then quicksort on, you know, an empty set of data to the right of the pivot. And, you know, quicksorting an empty list is fine, but we're going to quicksort this list, and when we do that, we're going to find our pivot 29 is in the proper location, so then we're going to have to make a quicksort call on this list. And what's happening is we're losing the idea that after one pass of our quicksort, we've split the list in half. In fact, what we're doing is we're cutting the list down by 1 each pass. The reason that we get an n log n out of quicksort is because, you know, one pass takes n operations, and if we split the list in half each time, we do basically log n passes. But if our data is close to sorted to begin with, then we may find that instead of doing log n passes, we do n passes, and each pass takes n operations, and our performance goes down to order n squared. And we're back to a bubble sort.
So, in theory, this would also be a problem if you have a maybe mostly sorted list, rather than just a perfectly sorted list. So, if we're dealing with, say, a wildly unsorted list, quicksorts would be better, right?
Yeah, quicksort will do better on unsorted data than sorted or partially sorted data.
Interesting.
What's really freaky is that, you know, most quicksort algorithms begin with a randomize operation. They'll take your data and they'll shuffle it up, just in case it happens to be partially sorted, because it'll actually run better with unsorted data than with partially sorted. That's got some interesting philosophy to it. Like drawing a painting on a blank canvas instead of one with like graph lines on it, you know. You'd want to like get rid of the graph lines first. Alright, other questions on quicksort?
That's crazy.
Alright, let's do a 5-minute break, and then I want to come back and talk about radix sort and talk about heap sort and heaps, and that will probably do us for the day. So let's come back at 14:05. All right, I'll see you back in about 5 minutes.
A really badly animated cat going. Oh, that poor bird's like, what the heck?
Sorry, bird. See if the bottom of that symbol is really wide. That would be harder.
We could add panels and make it wider. What if it went like out from the rim? Like on a different axis, right?
Yeah. Picturing some insane contraption covering it with hamster wheels, oriented like that. So it's just like,
Oh my god.
yeah, this is how wars start.
Yeah. man.
Oh, this is chocolate.
Yes.
Oh yeah, we knew that.
Uncle.
Welcome. All right, welcome back. Here's my random lounge music. Yeah, that was actually me on the piano. All right, so let's look at radix sort. So for a radix sort, we're going to treat our data as almost ASCII data, a series of digits. And so let me make some 3-digit numbers. All right. So I'm going to write out our numbers, and we're going to look at these digit by digit. And we're going to begin by looking at the least significant digit, so the one on the right. And we want to copy these into an output list such that the numbers are sorted by this least significant digit. And when we do this, we want to preserve the current order of this list as much as possible. So for example, these 3 numbers all end with a 9. I got to put them into the output list in the same order they're in right now. But they're going to come after the numbers that end with a 7 or an 8 or a 0 or a 1 and so on. So just looking at this rightmost column, right? I would want to put this number first, and then this one, and then the 7 and the 8, and then the 3 9s. So one way to do this, since we know there's only 10 possible values of digits, one way to do this sorting is to simply make 10 passes through this set of data. And the first pass, we're going to look for any number that ends with a 0. And if we find one, we're going to copy that to our output list. So it's kind of like a selection sort. Alright, once we've gone through our data, we'll make a second pass and look for everything that ends with a 1. And we only find one number, which is 401. And then we make a pass looking for 2s, 3s, 4s, 5s, and 6s. We don't find anything. Make a pass looking for 7s. There's a 407. And then make a pass looking for 8s. There's a 618. And then finally make a pass looking for numbers that end with a 9. And there's a 219, a 329, and a 229. Alright, and we're done with our first pass. So we're going to make 1 pass per digit. So for this set of data, we're going to make 3 passes. So next, we look at this digit in the middle. So let me just circle those digits. And again, we can sort this list by that middle digit by making another 10 passes. First pass, we'll look for things that have a 0. And this turns out to already be sorted by that middle digit. That was just coincidence. Alright, and then we make one more pass and we sort by the most significant digit. And so again, we can, make a pass, search for any 0s, search for any 1s, search for any 2s. So there's a 219, and there's a 229. And then make another pass, look for 3s, there's a 329. Look for 4s, there's a 401, 407. Look for any 5s, there's a 500. Look for any 6s, there's a 618, and there's no 7s, 8s, or 9s. And when we're done, our numbers have been sorted. So that's a radix sort. So questions about the procedure?
No, but this would be a great, fantastic way to just sort a billion books all at once.
Mm-hmm. So this is a fun sort to code, because you know there's not a lot of deep operations going on here. There's no recursion. It's a bunch of loops. So what about the order of efficiency? How much work do we do when we go through here and we pull out all the things that end with a 0 and copy those to the next output location? How many operations do we have to do roughly to go through n pieces of data, and anything that ends with a 0 copy to a new output location? Is it n? Is it n squared? Is it constant?
Is this an n squared?
For that one operation, it's actually just order n. If we have 7 pieces of data, I have to look at 7 pieces of data, and anytime I find something that ends with a 0, just write it down at the next output location. That's a good old order n. But I have to do that 10 times, right? I have to do that once for 0s, once for 1s, once for 2s, and so on. So, you know, one pass is order n, but I have to do 10 passes, so that's order 10n. And I have to do that for each digit. And so if we assume all of our numbers are you know, maybe 10-digit numbers, this is maybe 10 times 10n, this is 100n.
Wouldn't you have to multiply it by an order of magnitude for the greatest digits, maybe?
Tell me what you mean by that.
What if, in this instance, the greatest number in your data set had, I don't know, 2 digits, right?
Mm-hmm.
You could potentially have 10 to the 1,
Mm-hmm.
10 to the n.
Yeah.
Maybe I'm overthinking it.
Well, I'm thinking worst case, like if you had 10-digit numbers.
Right.
You do 10 digits, and for each digit you do 10 passes, and for each pass you look at all n numbers.
Oh, okay.
Right, so this would be, you know, order 100n. But we've said, you know, we throw away constants in the beginning. This is still order n. And so is this better than a quicksort? Because quicksort is n log n, and this is only order n.
Wouldn't it depend on the data set, actually?
It could. So here's the thing to keep in mind. These orders are what we call asymptotic limits. They're things that describe the behavior as n approaches infinity, as things get bigger and bigger and bigger. But you know, a bubble sort for 2 pieces of data might be faster than a quicksort for 2 pieces of data. Because quicksort, you got to do all kinds of work. You got to split things, move things around, you got to recurse, and so on. A bubble sort will probably be 1 pass. It might be, you know, a total of 4 operations, and we're done. And so even though a bubble sort is n squared, right, a particular bubble sort could be faster than a particular quicksort. But the other thing is this constant in front. Now if n gets really big, this constant goes away. Right? 100n will eventually be better than, you know, anything times n log n. But suppose I'm sorting 10-digit numbers. Right? So a 32-bit integer goes from 2 billion to minus 2 billion. So those are 10-digit numbers. And if I don't have repetitions of my data, at most I would have, you know, 4 billion numbers to sort. And a quicksort, which is, you know, order n log n. Well, log of 4 billion is approximately 32. So a quicksort would be roughly, you know, order 32n, whereas a radix sort would be roughly order 100n. And so even though it looks like, you know, the order might be better, and it would be better in the limit, right, for practical cases like, you know, sorting integers where we only have 4 billion integers to choose from, n log n is going to be better than a radix sort. So that's something you just keep in mind with these orders of complexity. They're really meant to describe what happens as the problem grows without bounds. So when n gets very large, how does one algorithm compare to another? That would be a fun project. Yeah, I like that. Alright, the other thing to note on radix sort, right, it's important when you're sorting by one digit that you don't perturb the order of things that have the same digit. Even though all three of these have 0, I don't want to write, you know, 401, 500, 407, because my final sort won't be right. So if numbers have the same digit in the position you're sorting, they have to go into the output in the same order that they appear in the input, which is still kind of like, you know, a selection sort notion. It's also a little counterintuitive sometimes that we start with the least significant digit instead of the most. Because, you know, if we want to compare numbers, a lot of times we look at the most significant digit. One is thousands, the other is 10,000s. The one with the 10,000s digit is bigger. But for this algorithm, we have to start with the least significant digit. That's just how it works. Alright, let's talk about heaps. So heaps are a really fun data structure, and we can use them to sort data. And rather than taking a set of data and turning it into a sorted collection of data, what we more often do with a heap is we feed in a bunch of data and we say, give me this data back from smallest to largest, or from largest to smallest. So it's kind of doing what a sort does, but the goal is not necessarily, here's a bunch of data, sort it and give it all back to me. It's, here's a bunch of data, give it back to me one piece at a time in sorted order.
Like a yield function, maybe?
Yeah, something like that. Alright, so how do heaps work? So a heap is a binary tree. And it has two essential properties. The first property is it has a heap shape. It's shaped like a heap. It looks like a heap. And we'll describe what that means. But the shape of the tree itself is the first criteria. And the second criteria is that every node satisfies what's called the heap property. And if both of those things are true, then this thing is a heap. Alright, so comment up front, there are two kinds of heaps. There's max heaps and there's min heaps. And they work identically to each other, except one deals with largest things, the other deals with smallest things. So yesterday's class we just talked about max heaps. So for completeness today we'll just talk about min heaps. But everything we say about min heaps will apply to max heaps, but we'll change largest to smallest and smallest to largest, and max to min and min to max. So it's all symmetric. Alright, so first of all, what is the heap shape? The heap shape basically says the tree is nice and full and fluffy. So here's a heap, right? Every layer is completely filled in. But if you don't have every layer completely filled in, you're allowed to have a few stragglers on the lowest layer, but they have to be filled in from left to right. So this would also be a heap. This would also be a heap. So would this, so would this. So would this. But if I suddenly hang a node off of here, or I hang a node off one of these nodes, it's no longer the heap shape. So the heap shape says, you know, every level meaning, you know, all the nodes of a certain depth, every level is full except possibly the deepest level, which must be filled from the left. So to satisfy the heap shape property, every level has to be completely filled except possibly the deepest level, which has to be filled in from the left. So this is a heap, this is a heap, this is a heap. This is not a heap, because the deepest level is not filled in from the left. But if I had nodes here and here, that would be a heap. And if I put a node here, that's also a heap. But if I put a node over here, it's not a heap anymore, because the deepest level is not filled in from the left. I need to go here, 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 here before I can go here. Alright, so that's the first requirement. It's got to satisfy the heap shape. The second requirement, every node satisfies the heap property. And so again, there's a min heap property and there's a max heap property. So min heap property says a node is less than both children. So we're going to think of a heap of integers just because it's easy to work with. And the min heap property will be that each node has to be smaller than its children. But there's no requirement for what sits to the left, what sits to the right. So a binary search tree, we know that everything to the left of a node is smaller, everything to the right is bigger. That's not the case with a min heap. With a min heap, the requirement is every node is smaller than both of its children.
I'm imagining max heaps are the exact reverse.
Max heaps are the exact reverse. Every node is bigger than both of its children. Again, we're not going to worry about duplicates. So here's an example of a min heap. Alright, this should be a good min heap. So it's got the heap shape. Every level is completely filled except the deepest level, which goes from left to right. And every node is smaller than both children. 10 is smaller than 20 and 25, 20 is smaller than 40 and 50, and so on.
I have a question.
Go for it.
it looks like it's pretty split about like the smallness of the right versus the bigness of the left. Was that on purpose or by accident?
That's just an accident, I think.
Okay.
Yeah, so I mean, I could have made this, you know, that's still a heap. Still a minheap. Alright, so we got the heap shape, we've got every node satisfying the heap property. So this is a minheap. And I'll just say heap property, but I mean, you know, in this case, the minheap property. If we were talking about max heaps, I would say heap property, and I'd mean max heap. But we'll stick with min, so every node has to be smaller than its children. Alright, so what do we do with a heap? We've got a heap, it's got a bunch of numbers in it. With a minheap, what we can do is ask for the smallest number. We can say, tell me the smallest number in the heap, and remove it from the heap. Alright, so first question, where in the heap would I find the smallest number?
Root, right?
It would be at the root. Why would it be at the root?
Because it's the children are always greater than the node.
Yeah, so the heap property guarantees that this number is smaller than both of these, and that heap property guarantees that this is smaller than both of those, and this is smaller than both of those, and this is smaller than both of those, and inequalities are transitive. If 5 is smaller than 10, and 10 is smaller than 20, and 20 is smaller than 40, we know 5 is smaller than 40. And so every node in here below the root has got to be bigger than the root. So the root is the smallest thing in a min heap. So how do we get the smallest thing? The value we want to return is the root of the heap. But if we're going to remove this from the heap, we're going to have, you know, an empty spot up there. So what should we put in place of that 5 in order to preserve the heap shape and preserve the heap property? Well, it's not clear how to do that up front. So what we do is first we try to preserve the heap shape. So I've got an empty spot up here at the root, and I'm going to take one of these numbers and move it to the root. What's the logical number to move in order to preserve the heap shape?
The smallest of the two children.
If I move the 7 up here, I'll have a hole here, and that won't satisfy the heap shape anymore. So forget the heap property, just think about the shape. But we're going to do what you said eventually. But
it seems like you'd do it recursively, like, you know, you'd replace the smallest with the smallest of its two children, and again, and so forth, so on and so forth. But it would probably disrupt the heap.
yeah, if we do that, we're going to end up, you know, with something missing over here.
Right.
So forget the heap property for a minute. Just think of the shape. What number could I move to the root that would still preserve the heap shape? And there's really only one answer.
Could you move one of the stragglers?
Which straggler?
Probably the smallest of the stragglers.
So which number?
40.
40. If I take this 40 and I move it to the root, do I still have a heap shape?
Yes.
Absolutely, right? The heap shape requires that every level is full and the deepest level is filled in from the left. So if I take the rightmost thing on the lowest level and I move that to the root, it's still shaped like a heap. And I've still got my first property satisfied. So we're going to remember what the root is, and we're going to return that eventually. We're going to move last node to the root, where by last node I mean the rightmost node on the lowest level. So I may as well write that. So rightmost node on the lowest level. We're going to move that to the root. So we're going to take this 40, we're going to put it up there. Well, we've got the heap shape, we've removed the 5, but now we have to worry about property 2. We have to satisfy the heap property at every node. And hey, we just took a number from the bottom of the heap and we put it up on the top. There's a good chance that's going to violate the heap property. So now we're going to do an go ahead.
You could probably take what was moved to the root and swap it in for the smallest child.
Yes.
You could probably swap the 40 and the 7 and not cause any problems, right?
Probably. So what we're going to do is what's called down heap. So we're going to down heap from the root. Okay, what does down heap mean? It means swap with, and for a min heap, we want to be smaller than both children. And so we're going to swap with, swap with the smallest child. Until the heap property is satisfied. So we'll start from the root and we'll say, is the heap property satisfied? No, 40 is not smaller than both children. So we'll swap 40 with the smallest child. So there's a 10 and a 7, we'll swap it with the 7. So 7 goes up here, 40 goes here. And now we're going to say, does this satisfy the min heap property? Is 40 smaller than both children? No, it's not.
No.
So we'll swap with the smallest child, 8. 40 comes down here. Now our 40 is here. Does that satisfy the min heap property? Yes, it does, because it has no children. And so we're done. And so our new heap looks like this. Let me draw it on a new sheet of paper. It's a 7, an 8, a 40, our big 900, a 10, 20, 25, and a 50 over here. And there we go, we still got a min heap.
Could you move back the function for 1 second?
Mm-hmm.
Thank you so much.
So the smallest value is always at the root. To remove it from the heap, take the last node, put it up at the root, and then down heap, which means keep swapping with the smallest child until the heap property is satisfied. If we get partway down and the heap property is satisfied, we're done, because we know that further down the heap property was already satisfied, and so we don't have to keep moving down. So we don't have to recurse. This can be done with simple iteration.
It's pretty satisfying to watch the down heap happen.
It really is. These are fun to do. They're more fun with like a whiteboard than with you know, crossing out. So let's do some more removals. So our first remove operation pulled out the 5. That was the smallest thing. The next time we ask for the smallest, it's going to give us a 7 because that's the root. So we'll take this out. We'll put the 50 up there. 50 is not smaller than both children, so swap with the smallest. 50 is not smaller than both children, so swap with the smallest. And there's our heap.
There's also a reverse operation I've heard called upheap, right?
Yeah. So let's go ahead and add something to our heap. So let me redraw the heap a little more neatly here. So we've got an 8, a 40, a 50, a 900, 10, 20, 25. That's what our heap looks like right now. So somebody give me an integer to add to the heap.
12.
12. All right, so to add to the heap, we basically do this in the opposite order. We put our number in the last position on the heap, so, you know, to the right of the rightmost thing on the lowest node, lowest level, or we start a new level if the lowest level is full, and then we're going to upheap. All right, well, our lowest level is full, so we've got to start a new level. So if we want to add a 12, we're going to put that over here on the left. We've still got the heap shape. And then we're going to upheap. So upheap, swap parent with smallest child, and move up until the heap property is satisfied. Alright, so compare a 12 to the 20. 20 violates the heap property. It's not smaller than both children. Swap with the smallest child. There's a 12. There's our 20. So come up here, see if the parent satisfies the heap property. Is 10 smaller than both children? Yes. We're done. And there's our heap. It still satisfies the heap property everywhere. It's got the heap shape, and we added a 20 to it.
Can I ask a question about maybe what the overall goal here is?
The goal is to be able to take a set of data and pull it out, in this case, from smallest to largest.
Yeah, but would this heap structure be good for turning into a BST, or
no?
What would its other uses maybe be?
So we would not build a binary search tree out of this. But if you have data that you simply want to pull out in sorted order, this is a convenient structure for that. And I'll give you an example, priority queues. So if you look on a typical operating system, there's job priorities associated with each thing running. So on my system right now, I've got 317 tasks. And these tasks come with priority numbers. So negative numbers are high priority, positive numbers are low. So the stuff that's owned by root tends to be higher priority. This job, which is my display driver, I think has really high priority. My user stuff has low priority. So when you're scheduling jobs in an operating system, typically, you know, you need to maintain a structure like a queue with all of your jobs in them. And you need to pull out jobs, you know, each time that you're ready to switch to another process. You pull out the next job in line, give it a little bit of CPU time, throw it in the back of the queue. But if you have priorities, right, you would have a separate queue for each priority level. And when you're ready to finish, you know, giving time to one job and you're ready for the next job, typically you want to find the job with the highest priority and give that a slice of time. And so you could take the priority of pending jobs and keep those in a heap. And if it was a max heap, right, the root would always tell you the ID of the job with highest priority that's ready to run. And so you pull that out, and then you know, the next thing at the root would be the next highest priority. When a job begins at a certain priority, it gets added to the heap. So you pop it in this location, you upheap, and you've always got your data structured in a way that it's really easy to find, you know, the largest or the smallest number by just pulling off the root. And this is a really efficient structure. We'll look at implementation and we'll look at order of complexity, and it's really efficient. And a binary search tree, right, if you want to find the largest number in a binary search tree, you start at the root and you keep moving to the right. And you go as far to the right as possible. Well, that's a log n operation, and it's less efficient than a heap where the largest number or the smallest number is always at the root. So again, depending on what you want to do with the data, different structures might make more sense. Alright, so if I add a number like, you know, 1,000, or, you know, let's say 100, I'll put it in the next location, I'll check the parent satisfies the heap property, I'm done. No work to do. Now I put in a number that's really small, like a 1, and I check the parent, it violates the heap property, so I'll swap the parent with the smallest child. And now I'll check this node's parent, and 10 violates the heap property, so I'll swap with the smallest child. And I'll check that node's parent 8, and that violates the heap property, so I'll swap that with the smallest child, and I've got a heap again. And in this case, you know, the thing I inserted was smaller than everything in the heap, and so that ended up at the root, as it should. Alright, so that's basic heap behavior, and again, this is all for min heaps. For max heaps, you still up heap and down heap the same way, but the up heap procedure would be, you know, swap the parent with the largest child as opposed to the smallest. Alright, other questions on that? So let's look at how we build a heap. Suppose you have a set of data and you want to turn it into a heap so that you can pull your data out in sorted order. Certainly one way to do that is to start with an empty heap and just add your data one number at a time. Make an empty heap, add your first number, add your second number, and adjust as necessary, add your third and adjust, and so on. This process of upheaping and downheaping, what's the order of complexity on that? If your heap has n pieces of data, how much work do you have to do to say upheap or to downheap?
Wouldn't it also be like a log n because you don't have to move through half the tree?
Yeah. So this is an order log n operation. The other way to think about that is the amount of work you might have to do to upheap is basically bounded by how many steps it takes to get to the root. Well, the number of steps to get to the root, that's the height. And height is, you know, on par with log of the number of things in your tree, if it's a full tree, if it's complete, which the heap shape tells us it is. And so n pieces of data, we have roughly, you know, log n levels, and that's the number of operations we might have to do, worst case, like when you insert something smaller than everything else, and you have to upheap all the way back up to the root. Well, we had to go 1, 2, 3 steps up. Well, that's the height of the tree also. So upheap, downheap is order log n. And if I wanted to build a heap by just inserting a number and adjusting, insert a number and adjust, and do that n times, right, I could build an entire heap in roughly order n log n. And that's not bad. That's the time it takes to build a binary search tree, for example, where you know, keep traversing down and inserting in the right spot. But there's a better way to build a heap. And this is by heapifying. And so if we have a set of data, we can turn it into a heap with a slightly different algorithm. So shout out your favorite, you know, 1, 2, or 3 digit integers, and let's build a heap out of them.
1.
That's sad. Only one favorite integer.
6.
6.
29.
29.
30.
30.
17.
17. Awesome.
2.
2. Got a 12 from a dead Mike. Cool.
685. Can you hear me now?
685. Yeah, I can hear you now.
Okay.
I'll go with 44 because it's 244. You know I'm going to go play the lottery with these, right? Alright, so there's a set of numbers, and what I've done is I've placed them into a heap shape, right? And there's no reason to believe this is a max heap or a min heap. We're still going to work with min heaps. There's no reason to believe that if we do this, we'll end up with a min heap, unless, you know, we got our numbers from smallest to largest. Well, that probably didn't happen because we just had people shouting out random numbers. And in fact, 29 is not smaller than both of these, and so on. But actually, this looks pretty close to a min heap. But we're not worried about that. The first thing we do is we take our data, we just arrange it in a heap shape. And now we do an operation called heapifying. And heapifying basically says start from a node and down heap. And we're going to do this for each node beginning with the last node in the heap, this 44 right here. Alright, well the 44, it has no children, it satisfies the heap property, I don't have to do anything. 685 has no children, it satisfies the heap property, I don't have to do anything. Same with the 12, same with the 2, same with the 17. I've gone through half my data with no work. And it didn't matter what these numbers were, they will satisfy the heap property. Now you get to a 30, and I say, does that satisfy the heap property? Well, it turns out it does. So now I go to the next number, here's a 29. Does that satisfy the heap property? This is for a min heap. Didn't know there was a question coming. So does 29 satisfy the min heap property?
It's too big, isn't it?
It's too big, so what should we swap it with?
44? Or yeah.
Gonna swap with one of these.
Oh, 2.
Oh.
Yeah, so swap it with the smallest child. So put the 2 there, put the 29 down there, and we're done. Go to the 6, does that satisfy the min heap property? Yes. Go to the 1, does that satisfy? Yes, we're done, we've got a min heap. Okay, so that one worked out kind of like, fortuitously. But let's look at a different example. Right, so suppose that's what our heap looked like. Alright, no children, this satisfies the heap property, this does, this does, this does. Let's go to the 30. 30 is not smaller than both children. I'm going to swap with the smallest child. And 30 satisfies the heap property. Come over here, 20 is not smaller than both children, so I'll swap with the smallest child. And now 20 has no children, satisfies the heap property. Come back up here to 40. 40 does not satisfy, so I'll swap with the smallest child. And 40 does not satisfy the heap property, so I'll swap with the smallest child. And we're done, and we've got a heap.
Okay, I'm pretty sure you went through this before, but I just want to make sure I'm fully understanding. So the min heap, the smallest is the root, and then as you go down, it gets a little bit bigger, but it's always going to be in descending order.
Yeah, so min heap, every node is smaller than both children. So the numbers will generally get bigger as you go down.
Okay, I think I missed that earlier. Thank you.
Okay.
I'm curious about something.
Yeah.
I noticed that you started from the middle and then went to the top and then did it that way. So I suppose that when you're doing this kind of organization, you start from the bottom low and then kind of like recursively work your way up.
So I actually started with this number down here, but it had no children, so it satisfied the heap property. Same with this, same with this, same with this. So you're moving from right to left and then slowly from bottom to top. So I'll look at this, 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 and then those two, and then this one. But thinking about it like that reveals something really cool, which is that, this bottom row of data, none of these have any children. And so they automatically satisfy the heap property. The only really time we have to spend is doing this down heaping. And the amount of down heaping work you have to do depends on where you are in the tree. If you're at the root, you might have to do, a lot of work to down heap all the way down to a leaf node. But if I'm already sitting at a leaf node, I satisfy the heap property. I don't have to do any work for these. Well,
so does that mean if you're actually coding one of these, you don't actually have to look at the leaves first? You can look at the level above it?
You could, yeah. So what does this mean time-wise, right? This means that half my data I don't have to do any work on. Taking random numbers and just throwing them into a heap shape, roughly half my data is already where it needs to be. Don't have to do any work. If I move up one level, these might not be in the right spot. They've got children, they have to satisfy the heap property. If they don't, I have to do some work. But how much work do I have to do if one of these numbers does not satisfy the heap property? One operation. I might have to swap with a child. And once I do that, I will be at a leaf node and I won't have to do any more work. So a quarter of my data requires one operation. Half my data requires no operations. A quarter of my data requires one operation. An eighth of my data requires two operations, worst case, and so on. So right here, I've got 7/8 of my entire data accounted for, and I might have to do two operations to down heap. Most cases, I'm not going to do any operations. Sometimes I'll do one. So even though it potentially looks like an n log n operation, the number of nodes where I have to actually do log n operations is just one. Right at the root, I have one piece of data which is going to require log n operations. Most of my data, I don't need any operations. So if you do the math, and this is some fun infinite series with powers of 2, negative powers of 2. If you do the math, the time it takes to heapify a set of n data and turn it into a heap ends up being order n. And that's really sweet. Right? So n operations, we can turn n pieces of data into a heap. And that's better than n log n for, say, a binary search tree.
Are we about to hop off for the SLP?
Yeah, I think so. Probably like 3 minutes.
So could you quickly go over the structure of that one more time, maybe?
Of heapifying?
Of the SLP presentations, like, are we just...
You'll go in a breakout room, you'll take turns with the people in the room presenting, and other people will come in and leave as they choose. So you might be presenting to, you know, just the other people in the room, the other students, or there might be people in there that are coming in from outside. But go to that Zoom link on Canvas, and Izad and I will be there, and we'll put you into a breakout room.
Gotcha.
All right, heap questions. Yeah, you'll present for basically 2 hours, but taking turns. So if there's 3 people and it's like, you know, 10 minutes each, it'll be a few presentations. But if nobody's in there other than students, we won't know if you're actually presenting, so, you know, you can goof off theoretically. But at least present to the other people in the room once or twice, because you want a chance to talk about your project, right?
Would it be cool if we took like 5 minutes to talk and then maybe ask some questions and then talk some more, maybe?
Yeah, so hopefully when you're talking, other people will be asking questions of you. But yeah, you know, do your presentation, which is, you know, maybe 5 minutes, and then see if people have questions. And these get really fun, you know, when you've got somebody in there who's interested in what you're doing and can ask you some good questions, maybe ask you things you haven't thought about or give you new ideas. That's the real benefit of this, and that's where it gets pretty interesting. All right. So Thursday I'm planning to spend mainly talking about the final exam and questions and doing some review. But I also want to talk about one more aspect of heaps on Thursday, which is how we implement heaps using arrays. And it turns out there's a really slick way to build a heap in code using a plain old array like CSE222B style. And it works better than using, you know, struct nodes with pointers and things like that. So we'll talk about that Thursday, and then we'll mostly spend Thursday just doing kind of review, question and answer. So definitely bring questions on anything from the course or outside to class Thursday, and we can talk about it then. All right, I'm going to close out 5 minutes early. Take a look on Canvas under the SLP presentation section. There will be a link to a Zoom session. Hop into there. I'll meet you there, and we'll go into breakout rooms and talk about SLPs for a couple of hours. All right, so I'll see everybody in there in a few.
Thanks.
Thanks.